So today we start with the chapter, not start, we're continuing with circles. So today we'll do nothing but the theorems. Okay, now what I have seen is that there are 23 theorems. So what I have decided to do is 11 in the first video and 12 in the second video. Okay, so this is the first video and we'll do 11 today. So here's the first theorem. So we'll start with this. So this is the theorem statement: a straight line drawn from the center of the circle to bisect a chord which is not the diameter is perpendicular to the chord, meaning that whatever this is a line that is drawn to the center and this is one chord. Now if you draw a line that is bisecting the chord, that means you have to show that this is perpendicular. Let's try to show this. Let's say this is the circle, this is the chord, this is the line. Okay, this is the center. Obviously I'm joining this. Now I know that this is equal to this. Okay, I have to show these two are perpendicular. I'm not drawing this now. Now we know these two are radius and all radiuses are same, so this will be equal to this. Now this side is common between both of them, so obviously these two become congruent. So this, if that is congruent, that means let's say A O B C. So AOB equal to AOC. Understand? So, and we know what AOB plus AOC equal to 180. So replace any one of these here. So AOB equal to 180. So AOB will be nothing but 9. One second, let me rewrite this. AOB will be nothing but 90 degree. So this also will become 90 degree. So these two become perpendicular. Understand this first theorem? So let's move on to theorem. One second. Theorem 2. Theorem 2. Okay, theorem 2 I'm not going to show because this is just the converse of theorem 1. I'm just writing converse. Converse means exactly opposite. Okay, meaning what was theorem 1? Let's see. Straight line drawn to the center of the circle to bisect a chord which is not a diameter is perpendicular to the chord. So now we have to prove that a straight line drawn from the center that is perpendicular to the chord also bisects the chord. Understand? So let's prove it. Let's say this is the circle. Here this is the chord and this is the, let's say this is the thing passing through the center. Okay, so now we know what this is perpendicular. Okay, and now we also know this is R and this is R, so this is equal to this, and this obviously is a common side. So now by RHS this triangle is congruent to this triangle, so by CPCT this side will be equal to this side. It was easy proof. Okay, 2 theorems done. Let's go to the third one. So let's do theorem number 3. The statement is that equal chords of a circle are equidistant from a center. Okay, so we know that these two chords are equal, and I have to prove these perpendicular bisectors on each side, means the perpendiculars drawn from the center on each side are equal in length. So let's say this is the circle. Okay, these are the two chords. Let me draw the first chord better. Yes, this is the center. Now we'll draw the perpendiculars. Now what we know is this part. If we draw this, okay, this is R, this is R, so this is equal to this. Understand? Now as you can see that here you can see, so as I was saying, this is R, so this is R. Now see, this angle is equal to this angle, so I got a hypotenuse that is equal, the right angle that is equal. I need a side now. Now you know what, these two chords are equal, so let's say these length of these two are x. Now these are perpendiculars. Now remember the first theorem that said if there is a perpendicular drop from the center onto a chord, then it is divided, it is bisected. So this, let me rewrite this x, so this part will become x by 2 and this part will become x by 2, so this will be equal to this. So I got a side, so these two become congruent. Now if this is congruent by CPCT, you can say this side is equal to this side. Understand, this is my theorem 3. Now let's move on to theorem 4. Now the chapter is framed like that if you the theorem 4, theorem 3, the 4 even numbers are actually nothing but the converses. This is nothing but the converse of theorem 3. So what the theorem 3 state, equal chords of a circle are equidistant from the center. So chords that are equidistant from a center are equal. We have to prove this. Now I know this proof maybe seem trivial, but I am doing it for sake you understand. So these two are the chords, let me say. Now we know what they're equidistant means. This is equal to this. Understand? If you draw this, I draw this. Okay. So this is equal to this. Both are radiuses. Now this one will be side. Got a side, we got a hypotenuse, we got a right angle, RHS. So this becomes, these two become congruent. So by CPCT, this side is equal to this side, and we know these are perpendicular. So this side will be equal to this side. So this side, let's say this is A, then this will also be A, and this will be A by theorem 1, that whenever a perpendicular is dropped, it bisects it. So this both the chords are 2A, so both the chords are equal in this case. So what did we prove now? That that when two chords are equidistant from the center, they are equal chords. Let's do the theorem number 5 now. Theorem number 5. Now theorem number 5 says that a tangent to a circle and the radius, let's say the radius and the tangent, they're perpendicular to each other. Radius and tangent are perpendicular to each other. So how do we prove it? Very simple proof. Let's say this is the circle, this is the tangent, now this is the radius. We don't know perpendicular. So now let's take any point Q. This is O, this is P, let's say Q, and join this. Okay, now as you can see, except P, all the points are on the exterior of the circle. Now think about this. If there is a circle here, if a point that is on the circle and a point that is on outside the circle, which is from the center, which has the greatest OS OR, which is greater, you will always say that OS is less than OR because that is on the exterior side. So now in that manner also OQ, all this Q points here, this will be outside. So I can say what? OP is less than all such OQs. Understand? That means what? OP is the smallest line. OP is the shortest line. Actually, OP is the shortest line that is can be drawn from the center onto the tangent. Okay, so now we know that the shortest segment that can be drawn from a point on a given line is the perpendicular for the given point. Means this is a fact you should know. I am not going to tell you anything now. If there is a line, there is a point, always the shortest distance is nothing but the perpendicular. Okay, so I can say that OP is perpendicular to the tangent. Understand? OP is perpendicular to the tangent then. So let's move on to theorem 6, I guess so. Now what theorem 6 says, that whenever there are touching circles internally or externally, then obviously the center, the line, there is a line that joins the center of both the circles and the point of means wherever they touch the tangent, like this. If there is internally touching, let's say, and externally touching, see, these are the center and this is the meeting point, they will lie on the same line. This is the line, this is the center of this is the center of this, they lie on the same line. How to prove this? So let's say this is case 1, this is case 2. Let's prove case 1 first. One second, let me redraw. Yes, this is the center. Let's say A, P, B. Okay, APB. Now let's say I join this line, I join this line. Let this angle be alpha, let this angle be beta. Now what did we learn earlier? That the radius is always perpendicular to the tangent. So alpha will be nothing but 90. Same way beta will be nothing but 90. You'll see, this is the tangent, this is the radius, this is tangent, this is the radius. So what is alpha plus beta? 180. So this line, this is 180. So this thing is nothing but a straight line. Okay, because if there is this part and this part, if they're 180 to each other, this is nothing but the same line. Understand? Now let's do case 2. I can't draw this type of circles. Okay, this is, let's say, B, this is A, this is B. Now what do we know? X, let's say XPA is equal to 90. So XPB equal to also 90. We know how. Obviously for this triangle the tangent is this, for the big triangle also tangent is the same thing. So both cases the radius will make 90. So I can say XPA and XPB both are 90 degree. Now let's say, one second. Yes, let's say there is one line here. If I say this X P XP, let's for example, and there is, let's say, A and B, 2 points here. If I say XPA is equal to XPB, so obviously XPB has to pass through A. So this thing becomes one straight line. So BAP is a straight line. BAP is a straight line. So both cases I said you that this thing passes through the same line. Okay, now one second, what number theorem was that? Theorem number 7. We'll do theorem number 7. Theorem number 7. So this theorem is the most important, once again, most important theorem. Angle subtended by an arc of an angle subtended by an arc of a circle at its center is double the angle subtended by any point of the remaining triangle. Meaning what? That if there is a circle like this, one second, if there is a center and any part, okay, let's say, so this part, whatever the angle may be, let's say it's theta, so this angle will be nothing but theta by 2. They'll say just lying, it's not possible. Yes, it's possible. Okay, it's possible. How? Let me show you the proof. Let's say this is a circle. Okay, now let's say this is the center. I draw this here and I draw this here and I draw a line through this. Okay, just a line joining this point and this point. Okay, now let's say this angle is alpha, this angle. Oh, my screen crashed, so I have to do it again. I'm just doing this part. Okay, so here let's say this is the center and this I'm drawing like this. Now let's try, we'll draw any line passing here, passing this through this point and this point. So let's say this angle is alpha, so this also has to be, let's say, beta. Agreed. Now can you see this line is equal to this line equal to this line? Okay, because why? That all are radiuses. Now let's enlarge this. Enlarge the left side. The left side looks something like this. This is alpha. This is equal to this equal to this. So let's say this is x. This is x. Now by the exterior angle property, we know what 2x is equal to. No, I'll not write 2x. Maybe hard for you people. X plus x is equal to alpha. So x is nothing but alpha by 2. Same way if we do our right side, so this is beta, so these two angles will nothing be but beta by 2 and beta by 2. Same way, no? So if you go to the original diagram, I found out what this angle is alpha by 2 and this angle is nothing but beta by 2. Okay, so can't you see? So what is this angle totally? This angle is nothing but alpha plus beta by 2 and this angle is totally what? Alpha plus beta, meaning what? It became double. Means, can you see? So this is actually half of this. Understand? This was theorem number 7. People understand? Today I'm going to do 12, not more. 12 or 11, let me check, I don't know. So this is theorem number 7, so we'll do now theorem number 8. Theorem number 8 is actually a follow-up. It says that, so theorem 8 is nothing but if there is this arc with any line you draw like this, any that is touching one point here on the circumference, the angles will be equal. How you would say? Now let's say there is a circle, this is the center, this is 2 alpha. Let's say I draw here, I draw here, I draw here. For this it will be alpha, because last time I told you for this alpha, for this alpha, because see, same arc with this here, with this here, with this here. So for any like this such triangles, it will always be alpha. Okay, understand? So all such things from a single arc will from any point will yield a same angle. So now let's do theorem 9. Okay, theorem 9 is nothing but the converse of theorem 8. Converse of theorem 8. Okay, so theorem 9 says that if, one second, if there's a circle, okay, and let's say there is any 2 points, even this point can go outside, if their angles are same like this alpha, then this point will lie on the circumference. That's what we have to prove. So we have to break it by cases. So if we see like this, if this is the arc, if this is the arc we are dealing with, and let's say one we know this inside alpha. Okay, so now let's say we have one point outside, we have one point inside. Okay, we know this is alpha. Understand, this is alpha by question, and now by the earlier theorem you also know if this is alpha then this is alpha. Understand? Then if this is alpha, that means that this thing, let's not give this type of example, I'll do it in a different way. Let's say there is a circle here, this is the arc we are dealing with, and let's say this is here and one is outside and this is just touching here. Okay, now we know what this angle is alpha, so this angle has to be alpha by question, but by the theorem earlier we learned this is alpha. Okay, so now let's say if there is a line, there is one point here, can it ever happen on one side of the line that when you draw two lines they will have same angles? Can it? Yes, it can happen if they both 1 second, let me try redraw this. Okay, it can only happen if both are on the same line, means these two lines are not distinct. So these two lines will not be distinct but be the same line, so this point will nothing be but on the circumference. This is case 1 when the point is in the exterior. Now let's say if the point is interior, let's say like this is the point. Now by the question we know this is, let's say, theta, so this has to be theta, but by the theorem earlier we learned that is theta. So in the same way, can that line, I'll not explain it, this cannot be equal to theta, alpha or theta. If this alpha theta, alpha not equal to theta obviously, but here it is becoming equal, so there will be a contradiction. So this line will be nothing but this line, so the point has to be on the circumference. This is case 2 for interior. Understand, this is a little bit tough to understand, but if you don't understand this proof, no problem, this seldom comes. Okay, so what did we do? Theorem 9, theorem 10 now. Theorem 10. Angle in a semicircle is a right angle. This is a semicircle. If we draw any angle like this will become a right angle. Now you would say why? This is the proof. So let's say there is a semicircle like here. So if this is the diameter, so this part is actually the semicircle. So now let's say if we draw like this angle is nothing, if this is the center, this angle is nothing but 180 degree. And now remember what I said, angle subtended at the center is double of the angle subtended on any point on the circumference. Means what? If it is 180 by 2, this point has to be 180 by 2. And what is 180 by 2 if you know? That's a 90 degree. So this will become a right angle triangle, more appropriately a square here. Understand why? So now theorem 11, this or the next one may be last. If it has 11 has a converse, I'll do it. If it does not have a converse, I'll not do it. Okay, 11 itself is a converse, so 11 will be the last for today. So this is the converse of nothing but the 10. Converse of 10. It says that if like this is a 90 degree angle, if the arc of an circle subtends a right angle at any point, the remaining part of the circle, then the arc is a semicircle. Now how will you prove this? See, now let's say this is 90 degree, 90 into 2 is 180 degree by earlier theorem, so this has to be from the center 180 degree. So if it is 180 degree, then it's the diameter, and the diameter is passing through the center. No, it's actually a chord first. Okay, now the chord is passing through the center, that's why this is the diameter. And whenever like a arc of a circle passes the chord below it is the diameter, then this is what? A semicircle. So today I think I'm going to end it here. So please like, share and subscribe. Okay then, bye.